Good morning students. Today is lecture 1 under module 11 and as you know that module 11 is dedicated into 3 lectures and we will be learning about actually organic commodity chemicals that are being manufactured from the biomass. And in today's lecture we will talk about synthetic organic chemicals such as lactic acid and polylactic acid PLA. So, let us begin. So, biomass is utilized worldwide as a source of many naturally occurring and some synthetic specialty chemicals as well as cellulosic and starchy polymers. High value, low value products including many flavorings, drugs, fragrances, dyes, oils, waxes, tannins, resins, gums, rubbers, pesticides and specialty polymers are commercially extracted from and produced by conversion of biomass feedstocks. However, biomass conversion to commodity chemicals which includes the vast majority of commercial organic chemicals, polymers and plastics is used to only a limited extent. Biomass can serve as a source of large volume organic chemicals that retain the basic structural characteristics of biomass and either are or have the potential of becoming commodity chemicals. One such is actually very famous, which is dextrose or you can say D-glucose from the hydrolysis of starch or cellulose, high fructose corn syrup from the enzymatic isomerization of dextrose hydrolysate and D-xylose from the hydrolysis of the hemicellulases. These are commodity products. Biomass feedstocks present several opportunities for varying product distributions as a function of market demand and other factors or in which an optimum mix of products is chosen based on feedstock characteristics. Mild acid hydrolysis of hemicellulose in wood for example, affords a solution that is predominantly either xylose or mannose depending on the type of wood and a cellulose lignin residue. Now, acid treatment of this residue yields a glucose solution which can be combined with mannose for alcoholic fermentation and a lignin residue. If you recall these things we have discussed when we had discussed about fermentation products and all these things, okay. But here we will discuss about specialty chemicals in detail. Now, phenols can be made from this residue by hydrogenation and 2-furan carboxyaldehyde that is furfural can be made from xylose by strong acid treatment. The commodity chemicals obtained from the primary biomass feedstocks C5 and C6 sugars and lignins in this system design are ethanol, furfural and phenols. Other compounds that can be produced directly from biomass in good yields, but which do not retain the basic structural characteristics of biomass are classified as commodity chemicals. So, examples are many as in the beginning of the class I told you. Okay. Some of the major important things are acetic acid, methane and synthesis gas. Now, they are not manufactured in large volume from biomass because fossil fuels are the preferred feedstocks in commercial production systems, but as you know that fossil fuel is depleting and there is a need to look for alternate fuels and of course, a route for producing even commodity chemicals. So, biomass has taken a center stage of research since almost 20 to 30 years. Now, technically biomass can serve as a feedstock for production of the entire range of commodity organic chemicals presently manufactured from fossil fuels. Naturally occurring organic chemicals have long been extracted from a variety of biomass species. Alkaloids, steroids, vitamins, amino acids, proteins, enzymes, oils, gums, resins, waxes and other complex organic chemicals are isolated and marketed as specialty products or used for the conversion to other specialty products. So, thousands of examples exist, okay. Just something I have written here, we will go through it, okay. The glycoside digitonin used in heart medicine from the purple foxglove plant, the narcotic morphine from the opium poppy plant, the anti-malarial quinine from the tropical trees of the cinchona species, the chemotherapeutic agent Taxol from Pacific ye tree members of the genus Taxus, the algenes and alginic acids from the ocean kelp Macrocystis pyrifera, the high erucic acid canola oils from the rapeseed, the lascarella oils that are high in hydroxy unsaturated fatty acids from cruciferous lascarella species, the B vitamins from various biomass species, the alkaloid scopolamine from the belladonna plant, the enzyme cellulase in certain bacteria that catalyzes the hydrolysis of cellulose to glucose etc. Okay. Now, all of these specialty products are organic or organometallic compounds and most are normally marketed as high value and specialty products. Now, having said that, we just try to understand actually that these are some of the names only, there are many, right. But again I have told you many times that what happens when you produce something from the biomass. Biomass itself is extremely complex in nature, we have learned that. Okay. So, when you degrade it, try to make some value added products out of that, does not matter whether you use thermochemical conversion process or you use biochemical conversion, that is fermentation. The major problem is of course the downstream processing. Okay. Another problem is of course the extraction of that particular compound from which you are going to make some value added products. This is first step. Second is their purification or downstream processing part. So, which is extremely, we can say that it is costly with respect to the chemicals required, the equipments that is being required, and of course the energy, right. So, people are working day and night on that those aspects. We have already learned some of the latest developments of downstream processing part, and again we will also discuss in future about downstream processing. Okay. So, these commodity chemicals, their structures are complex, only a few are semi synthetic or synthetic products. The retention of chirality by natural organic chemicals used as pharmaceuticals, dietary supplements and biological agents is beneficial because physiological activity depends on it. Now, the majority of complex organic chemicals that occur naturally in biomass will therefore continue to be obtained by extraction of suitable species. This is what I was just mentioning. Okay. The need for development of a particular protocol to extract suitable species, okay, that too in a cost beneficial or economical way. So, when the cost of synthesis from the biomass feedstocks is acceptable and competitive. So, cost is very important, that has to be taken care when you go for making commercial production. Now, chemicals from wood or silvichemicals are in class by themselves. So, many silvichemicals are commercially available. Natural polyisoprene rubbers from trees that are members of the genus Hevea continue to be harvested and marketed, that is in large scale. Now, turpentines supply fragrances, perfume ingredients, aroma chemicals, flavorings and a large number of terpene intermediates for the synthesis of high value chemicals such as vitamins. Synthetic terpene resins prepared by cationic polymerization of terpene hydrocarbons are used in hot melt and pressure sensitive adhesives. Wood pulps are sources of specialty sugars as used in drugs, sweeteners, plasticizers and surfactants. In addition to the commercial regenerated cellulose described previously, wood pulps are used for production of cellulose esters such as the acetates and butyrates for fibers, films and moldings, and for production of ethers such as ethyl cellulose, carboxymethyl cellulose and hydroxymethyl cellulose for use as gums and thickening agents. The alkaline pulping liquors are usually combusted to recover the pulping chemicals and energy for recycle, but the alkali lignins are also separated for use in formulating resins, rubbers and emulsions. Dimethyl sulfide, dimethyl sulfoxide and dimethyl sulfone are recovered from the volatile fraction of the craft black liquors from the sulphate pulping. The sulfonated lignins in sulphide pulping liquors are a source of semi-synthetic vanillin and are separated for use in formulating adhesives, binders, dispersants, tanning agents and similar products. The alkaline pulping liquors yield fatty and resin acid salts that on acidification afford tall oil fatty acids for conversion to dimer acids, polyamide resins and other products that are used in inks, resins, adhesives and surface coatings. Now, phenolic acids and waxes extracted from various barks are used in a variety of resin applications. In the midst of the fossil fuel era, the less complex commodity organic chemicals are preferentially manufactured from petroleum or natural gas, whereas complex specialty chemicals are derived from biomass. Okay. But commodity organic chemicals are open to entry by biomass feedstocks if they can provide economic advantage. Again the same thing, that economic advantage is coming into picture. Okay. So, when you talk about economic advantage vis-a-vis biomass, again I am just trying to repeat it, that two things are very important. The species which you want to extract from the biomass, that step has to be economical. Okay. Then second is that once that is produced, mostly they will be in aqueous phase mostly. Okay. Then you have to go for purification, that is the downstream part. So, both these steps are the major contributor to the overall cost of the final product. Okay. So, note that many of the routes described here to commodity chemicals from biomass were in commercial use in the past, are still in commercial use, have recently been commercialized or have been developed and are available for commercial use. So, this is actually you can see what are the different types of this one products or value added products that can be derived from the biomass. These are all commodity chemicals only, we are not talking about other things like here this one directly as biofuel and all. So, you can see that C5 sugar, C6 sugar, cellulose, lignin, okay, and other things. So, nitrogen and carbon. Okay. So, from the C5 sugars we can have furfural and xylitol. From C6 sugars you can have so many things. So, ethanol and so many other things, of course, ethanol is of course goes to your biofuel production, but we are discussing about commodity chemicals. So, you can see all the chemicals here, different types of acids. We can have glycerol and all these things as their byproduct, can also be converted to some other value added products. Then you can have fructose, very important. Okay. Similarly, from cellulose we can have different types of acids, esters, nitrates, ethers. Okay. Then from lignins, the main thing is of course phenol, phenolic compounds and vanillin, okay, and lignin sulfonates. Then there are so many other things also. So, the primary building blocks and the main processing methods for production of the more important biomass derived chemicals are given here. Okay. So, we will see the different commodity chemicals by various routes. First, we will talk about the thermochemical synthesis. Consideration of the building blocks for most organic chemical commodities, the synthesis gas, the light olefin ethylene, propylene, butadiene and BTX, and the chemical structures of the principal biomass components suggest some of the routes that might be developed to provide improved thermochemical processes for biomass feedstocks. With the exception of synthesis gas, each of these building blocks in a hydrocarbon, whereas the principal components in biomass, the polysaccharides, are polymers in which each carbon atom is bound to an oxygen atom. Depolymerization and carbon oxygen bond scission are therefore necessary on a large molecular scale to synthesize the same building blocks. Such brute force degradation can be achieved at elevated temperatures, but there are opportunities to employ thermally balanced processes and energy conservation and to transfer the carbon and chemical energy in the feedstock to the desired products at a near theoretical yield. Low moisture content feedstocks are clearly preferred for thermochemical processes. This we have understood earlier also when you discussed about thermochemical conversion processes in detail, such as gasification and pyrolysis. Now, also the costs of producing the basic building blocks from biomass feedstocks by thermochemical methods are usually more than the costs from petroleum and natural gas, and that is the problem. Okay. Now, this situation is expected to change as the fossil fuel era approaches its ends. Now, when that happens, you will never think about cost. However, cost is always an important factor when you talk about commercial production in a sustainable way. Now, thermochemical gasification of biomass to high yields of synthesis gas or syngas can be carried out with most biomass feedstocks without regard to the structure of the biomass components. All of the organic components are thermochemically gasified under conditions that yield the desired syngas composition. Syngas in turn can be converted to a large number of chemicals and synthetic fuels by established processes, okay, such as you can see the scheme, okay, such as the BTUs, hydrogen, methanol, SNG, okay, ammonia, oxaloalcohols and different types of hydrocarbons. The gasification technology for conversion of biomass to syngas has been developed and scaled up from the laboratory to the pilot plant to full scale systems. If you recall, we have discussed some of the success stories, okay, how it has been adapted in India as well as other countries. Now, it has been commercialized for fuel production, but not for the manufacture of syngas derived chemicals, but there is no technical reason why commercial syngas processes cannot employ biomass feedstocks. Okay. Time has come that it has to be done. Now, the competitors for biomass feedstocks are natural gas and petroleum feedstocks, which are currently preferred in most countries for syngas production and conversion to methanol or high hydrogen streams for other applications. The direct thermochemical production of the intermediate light olefin building blocks from biomass can be achieved by rapid pyrolysis at temperatures above those normally used to maximize liquid yields. Maximum liquid yields occur near temperature of 500 degree centigrade. The volatile matter formed by biomass pyrolysis begins to participate in secondary gas phase reactions at temperatures exceeding about 600 degree centigrade. Using gas phase residence times of 0.5 to 1 second at temperatures above 500 degree centigrade, the apparent rates of gas production from cellulose were measured for 7 gas species: carbon dioxide, hydrogen, carbon monoxide, methane, C2H4, C2H6 and C3H6. Now, first pyrolysis of biomass by the RTP process for example provides reasonably good yields of light olefins at reactor temperatures and residences times of 700 to 900 degree centigrade, and of course 0.03 to 1.5 second. You can understand very fast. Okay. Now, the gas yield can exceed 98% of the biomass. Optimum yields of ethylene, total gaseous unsaturates and total gaseous hydrocarbons from woody feedstocks were 8, 15 and 25% by weight of the feedstock. BTX and syngas are the byproducts. Another method for production of ethylene and propylene from biomass feedstocks is via syngas and the synthesis of Fischer-Tropsch hydrocarbons. Now, if this technology is commercialized on a large scale, at some future time the resulting hydrocarbons can be readily converted to these olefins, and that is going to happen in near future. So, almost any paraffinic or naphthenic hydrocarbon heavier than methane can be steam cracked to ethylene and propylene in good yields. Now, the lower molecular weight paraffins normally afford higher yields of ethylene, whereas the higher molecular weight paraffins yield products that have higher propylene to ethylene ratios. An approach to the production of ethylene from biomass that does not involve pyrolysis is of course your ethanol dehydration, and the catalytic conversion of syngas to ethanol from low grade biomass or even fossil fuel feedstocks, and fermentation ethanol via advanced cellulose hydrolysis and fermentation methods, which make it possible to obtain high yields of ethanol from low grade biomass feedstocks as well. It is a good process or technology. Okay. So, what is important is that these processes are expected to make large quantities of low cost ethanol available for chemical uses that include ethanol conversion to ethylene as well as acetaldehyde and acetic acid. Once this technology is operational for the production of these chemicals, an entire commodity chemicals industry founded on low cost ethanol can follow. A complete biorefinery approach you can say. Okay. Sustainable biorefinery. So, markets forces will determine which low cost ethanol technology is superior. Each is anticipated to be capable of providing ethanol at market prices in the same price range as methanol derived from natural gas. Butadiene is manufactured in the petroleum industry by the catalytic dehydrogenation of the butanes and butenes and by the direct cracking of naphthas and light oils. The overall butadiene yield by catalytic dehydrogenation, the most common industrial process, is as high as about 80% at selectivity of about 90%. The yields and selectivity of butadiene by direct thermochemical conversion of biomass are nil, and the various routes to C4 hydrocarbons from biomass are not yet practical. A few options exist for butadiene synthesis by alternative methods. Processes based on each of these routes to butadiene have been developed and commercialized. Butadiene is obtained by the following chemical reactions. Ethanol is the key reactant in equation 1 and also in equation 2 because it is readily converted to acetaldehyde. The processes based on equation 1 was developed in Russia, and the process based on equation 2 was developed in the United States. Okay, these are the two reactions you can see. The yield of butadiene for the Russian process is about 30 to 35%. It is about 70% if the mixtures of ethanol and acetaldehyde are employed as in the US process. Equation 3 represents a process that involves 2,3-butyne glycol, a product from the microbial conversion of the biomass. The process is carried out in two sequential steps by the glycol diacetate in overall yields to butadiene about 80%. The process of equation 4 starts with a biomass derivative, the cyclic ether tetrahydrofuran, and can be carried out at high yields. When this process was first operated on a large scale in Germany, acetylene and formaldehyde were the raw materials for the synthesis of intermediate tetrahydrofuran. In commercial practice, the aromatic building blocks for the synthesis of commodity organic chemicals, particularly benzene and p-xylene, are extracted from BTX. BTX is a mixture of the monocyclic aromatic hydrocarbon, benzenes, toluene, ethyl benzene, and the xylene produced in the petroleum industry by the dehydrogenation of naphthas using catalytic reforming and by the thermal reforming and catalytic and thermal cracking of middle distillates. Coal tars and coke oven gases also yield BTX. In modern coal coking process, more than 90% of the benzene and toluene obtainable from coal is collected by scrubbing coke oven gas. The direct thermochemical conversion of biomass to an equivalent BTX product, however, is not feasible under conventional conditions. Only a small amount of the monocyclic aromatic hydrocarbons are formed on pyrolysis or the thermal cracking of biomass feedstocks. The pyrolysis of pure cellulose yields many different liquid products, including a few substitutable phenolic compounds and phenol, only trace to small amounts of BTX are formed. Pyrolysis at atmospheric or reduced pressure of the lignins, which are highly aromatic structures because of the abundance of the substituted phenyl propane units, yields phenols instead of the BTX type of products. The hardwoods generally yield phenols in the pyrocatechol and pyrogallol series, whereas softwoods yield phenols in the pyrocatechol series. Now, a few of the aromatic compounds that have been identified in lignin pyrolysis products are phenol, eugenol, pyrocatechol, pyrogallol 1,3-dimethyl ether, ocresol, guaiacol, vinyl guaiacol and propyl guaiacol. Now, most of the methanol formed on pyrolysis of woody biomass might be expected to be derived from the large number of methoxyl groups in the lignin fraction, but a substantial portion is also believed to be formed from the methoxyl groups present in the hemicellulases too. Two basically different methods were found to maximize BTX formation during direct thermochemical conversion of biomass feedstocks. One is the hydrogenolysis of the substituted phenolic compounds that are formed from woody feedstocks, and the other is aromatization of intermediates. The non-catalytic hydropyrolysis of hardwood maple chips at 670 degree centigrade and 1.02 megapascal shows that aromatic compounds are formed in substantial yields on first pyrolysis in hydrogen atmospheres. The liquid product yield is about 17 weight% of the feed. Wandering aromatic compounds make up about 39 weight% of the liquid product, and the yield of phenol is about 26 weight%. It is evident that to increase the yield of BTX, hydropyrolysis at greater severity or hydrocracking and hydrodealkylation should be used to aromatize more of the phenolic compounds. This is just to increase your BTX yield. The organic vapors formed on first pyrolysis of either woody biomass or RDF can be upgraded with selective zeolite catalyst to selectively yield either BTX or C2C5 olefins. It has also been found that biomass pyrolysis oils can be catalytically upgraded to high BTX liquids after formation and collection. Products containing 23 to 38 weight% BTX and 19 to 35 weight% aliphatic gasoline range hydrocarbons are obtained by thermal treatment at atmospheric pressure and 330 to 410 degree centigrade. The selectivity for benzene is about 90% of the BTX with aluminosilicate catalyst. Molecular sieve and similar SAP selective catalyst exhibited high selectivities for toluene, the xylenes and other alkylated benzenes. An alternative approach to BTX from biomass discovered in the 1980s employs first pyrolysis of woody biomass in methane atmospheres, that is methanolysis. Okay. So, preliminary studies of the methanolysis of dry firewood particles in the presence of silica floor at 1 to 3 second residence time, temperatures of 1000 degree centigrade and pressure of 0.34 megapascal converted 12% of the available carbon to BTX, 21% to ethylene and 48% to carbon monoxide without net methane consumption. Thus, the building blocks for synthesis of commodity organic chemical synthesis gas, the light olefins ethylene, propylene and butadiene and BTX can be obtained from biomass feedstocks by thermochemical conversion. Now, we will discuss about some of the pentose derived commodity chemicals. An example is of course, xylitol. Okay. The pentahydric alcohol that is manufactured by the hydrogenation of the aldehyde group in the xylose. Now, one of the unique reactions of the pentose known since its 19th century cyclodehydration to yield furfural. Xylose for example, is dehydrated by acid treatment through one or two intermediates to form the furan substituted aldehyde in quantitative yield of the xylose. The reaction is industrially significant because it made the furans available on large scale from biomass feedstocks such as corn cobs, oat hulls and rice hulls. Now, many other feedstocks has also been used and reported. Now, the two principal furans from which many derivatives are available are the tetrahydrofuran and tetrahydrofurfuryl alcohol, both of which are manufactured from furfural. Furfural is converted by catalytic decarbonylation to furan by catalytic hydrogenation of the aldehyde group to furfural alcohol. On further hydrogenation of the furan ring to the tetrahydrofurfural alcohol and by oxidation of the aldehyde group to furoic acid. Now, furan is converted to tetrahydrofuran by catalytic hydrogenation and undergoes a large number of substitution and addition reactions. Tetrahydrofurfural alcohol undergoes catalytic dehydration and rearrangement to dihydropyran, which can be hydrogenated to tetrahydropyran. Tetrahydroporphyryl alcohol is also converted to levulinic acid, is one of the most important commodity chemical, okay, on treatment with dilute acid. Tetrahydrofuran has been converted to adiponitrile and adipic acid precursor in commercially two-step process via dichlorobutane. Tetrahydrofuran has also been converted to N-butanol in high selectivity, which simplifies and reduces the cost of purification, and to 1,3-butadiene via dehydration and hydrogenation. Both furan and porphyryl have been converted to maleic anhydride, another important class of platform chemicals, okay, with the former producing better yields and fewer byproducts. 4 major carboxylic acids such as acetic acid, formic acid, glyceric acid and lactic acid are formed under mild alkaline oxidation conditions from xylose. So, we will now discuss about some of the chemicals from the hexose derived, okay, that is derived from the hexose basically. Several hexose sugars, sugar syrups and starches are marketed as commodity chemicals, but only a few derivatives such as the disaccharide cellobiase, a glucose 3 glucoside, okay, which is synthesized not from glucose, but by careful hydrolysis of cellulose are marketed. The hexoses yield a wide range of esters, ethers, anhydro derivatives, and they undergo numerous rearrangements, substitution, isomerization, cyclodehydration and reduction oxidation reactions to further produce value added chemicals. Glucose is converted to gluconic acid by oxidation of the aldehyde group to a carboxylic group, and to the hexahydric alcohol sorbitol by hydrogenation of the aldehyde group, or to sorbitol and mannitol when invert sugar is used in place of glucose. Then to a large number of ethers by elimination of water such as 1,6-anhydroglucose, 2,4-anhydroglucose, 2-hydroxymethyl porphyryl. The hexoses can also be converted directly to levulinic acid and formic acid on acid treatment without isolation of the 2-hydroxymethyl porphyryl. Levulinic acid is a versatile chemical intermediate that can be converted through proven routes to higher value chemicals such as diphenolic acid, succinic acid, pyrrolidines, pyrrolidones and the agricultural chemical 3-amino levulinic acid. Gluconic acid, glucono and lactone from this acid, then sorbitol, sorbitol esters, sorbitants, okay, mannitol, mannitol esters, copolymers of fatty acid sorbitol esters and alkaline oxides and a few other derivatives are currently marketed as commodity chemicals derived from the hexoses. Vitamin C, that is L-ascorbic acid, is perhaps one of the best example of a commercially derivative of the D-glucose that is manufactured primarily by chemical synthesis. Now, we will talk about some of the lignin derived chemicals. Now, commodity lignin chemicals and their salts and derivatives are complex mixtures of compounds obtained from the spent liquors of the wood pulping industry. The lignins are sold for a variety of industrial and specialty applications, including adhesives, binders, dispersing agents, emulsifiers, cement and gypsum board manufacture, oil well drilling and road stabilization formulation. A few pure commodity chemicals are synthesized from the lignins. Synthetic vanillin, okay, a member of the catechol series, is one such example. The compound, a pharmaceutical intermediate and flavoring and perfuming agent. Among the synthetic methods are the alkaline air oxidation of the spent sulphite liquor from pulping operations, then the oxidation of the coniferal alcohol from pine trees, the conversion of guaiacol from catechol or wood pyrolysis oils. Then some lipid derived chemicals. Lipids or fats are found in seed and vegetable oils and the fruit pulps, okay, and of course, animal tallows and greases also. The vast majority are triglycerides, C6 to C24 fatty acid esters of the trihydric alcohol glycerol. Smaller amounts of the mono and diacyl glycerides and unesterified fatty acids are also present. Alkaline hydrolysis of the glycerides provide large amount of glycerol and the fatty acids as a commodity chemicals. The fatty acids of most industrial significance as commodity chemicals from fat hydrolysis or as derivatives are usually esters, that includes the saturated lauric, mysteric, palmitic, stearic, archidic, behenic acids, the C18 mono unsaturated oleic and ricinoleic acid and the polyunsaturated C18 linoleic, linolenic and eleosteric acids. Now, glycerol forms acetals, aldehydes, amines, ethers, esters and halides and can also be converted to acrolein and other derivatives. Glycerol is thus a versatile chemical that is useful in hundreds of applications, the most important of which are in alkyl resins and the manufacture of the explosive nitroglycerin, glycerol trinitrile. So, the ester is synthesized from oils such as cottonseed or soybean oil by transesterifying the glycerides in the oil with a methanol to yield the methyl esters of the fatty acids in the same manner that methyl biodiesel fuel is manufactured. The methyl esters are isolated and then transesterified with sucrose to yield a sucrose polyester in which 6 to 8 fatty acids molecules are bonded through ester linkages to the hydroxyl groups in the sucrose molecule. The liberated methanol is removed. The synthetic ester has many of the characteristics of and is a low calorie replacement for natural fats. Unlike the glycerides in natural fats, digestive enzymes are unable to metabolize the synthetic ester, it passes through the body unchanged. Now, we will talk about some of the protein derived chemicals. Proteins are widely distributed in plants and animals and consist of one or more polymeric chains of amino acids that are bound and peptide linkages. Usually, more than 100 amino acids are linked in the natural polypeptide. The polypeptide chains are converted to the amino acids by acid, alkali and enzyme catalyzed hydrolysis. More than 30 amino acids have been isolated from protein hydrolysates. The most common amino acids are the neutral acids glycine, alanine, serine, cysteine and then cysteine, threonine, valine, methionine, leucine, isoleucine, phenyl, alanine, then tyrosine, proline, hydroxyproline, tryptophan and asparagine. The basic acids includes arginine, lysine, hydroxy, lysine, glutamine, histidine and ornithine, and the acidic acids are aspartic and glutamic acids. Glycine, alanine and methionine are chemically synthesized. Proline, hydroxyproline, cysteine and cysteine are obtained from the protein hydrolysates. Proline and hydroxyproline from the gelatin normally of animal origin, basically from the collagen, and cysteine and cysteine from keratin protein of the animal origin. Now, we will talk about biopolymers. Now, excluding the polyisoprenes, that is the natural rubbers found in several biomass species, the main biomass constituents, the natural cellulose, hemicellulose and lignins, as well as the proteins and nucleic acids are biopolymers. Some are chemically modified and marketed, some are marketed as natural products. The major classes of biopolymers include the cellulose esters and ethers, chitin and chitosan, then hyaluronic acid, polyhydroxyalkanoates, silk and other natural polypeptides, starch esters, xanthan, dextran and other polysaccharides, synthetic polypeptides and polymers synthesized from primary biomass derivatives such as glycerol and other polyols and fatty acids. Several of these polymers are biodegradable plastics useful in packaging, molding and extrusion applications, yield biodegradable detergents, furnish films and coatings that are selectively permeable to specific gases and are highly water absorbing materials useful for moisture removal or lend themselves to medical uses. Microbial synthesis. Microbial processing by direct fermentation of primary biomass derivatives such as glucose can be used to synthesize a large number of organic chemicals. The cellular components that facilitate these processes are enzymes that the protein catalyst produced by the microorganisms. It is evident that most of the common chemicals listed are commercially available from the non-biomass sources. The molecular structure of the products range from simple compounds such as ethanol to complex compounds such as penicillins to polymeric products such as polyhydroxybutirates (PHB). Suitable substrates are generally monosaccharides and disaccharides and their original sources such as molasses, starch and cellulose hydrolysates. A wide range of biomass feedstocks is used for commercial fermentation systems. Examples are glucose for many different chemicals and products, beet sugar molasses for citric acid, hydrolyzed starch for citric acid, itaconic acid and xanthan gum, thin starch for ionophores and alkaline proteases, vegetable oil for terramycin, corn strip liquor for penicillin, soybean meal for vitamin B12. Some naturally occurring and mutant strains of Athrobacter, Corynebacterium, Brevibacterium and Nocaria species have been known to excrete large amounts of certain amino acids into the medium. An intensive research effort has been carried out over the last few decades to isolate and characterize enzymes generated by microorganisms and to produce and market cell free enzymes for use as catalyst in the synthesis of commodity and specialty chemicals. Among the commercial preparations are amylases, proteases, cellulases, glucose isomerases and oxidases, pectinases, invertases and cofactors. Now, we will discuss about lactic acids and of course, then polylactic acids, the two most important commercial or commodity chemicals. Lactic acid is an important commodity chemical and intermediate for producing alkyl lactates, propylene glycol, propylene oxide, acrylic acid, and of course PLA, the polylactic acid. Lactic acid has found applications in food, pharmaceuticals and cosmetics. In general, it can be stated that there is a need to develop new catalytic process for synthesis of lactic acid, not only from carbohydrates, but also from the lignocellulosic material, which is cheaper and more abundant compared to the carbohydrates. Since lactic acid can be made from different reagents such as lignocellulosic material, cellulose, carbohydrates, sugars, trioses, glycoaldehyde and glycerol, and the reaction conditions are relatively demanding, it can be easily observed that these reactions are usually complex, involving several types of transformations such as aldol condensation, retroaldol condensation, dehydration, 1,2-hydride shift, etc. Lactic synthesis can be summarized as follows. It is principally performed in two steps. First, polylactide prepolymer is generated in the first step via dehydration, followed by thermal depolymerization in the second step, which gives lactide. Besides consideration of lactic acid as a platform for commodity chemicals, the interest in lactic acid arose sharply with the development of the biodegradable polylactides, that is the PLA, polylactic acid, produced by polymerization of the dilactide derivative derived by self esterification of the lactic acid. Now, we will discuss how PLA is also getting produced. Now, lactic acid is commercially produced by fermentation of biomass, starting typically for example from corn derived glucose, right. Fermentation processes suffer from low productivity along with costly separation and several purification steps. That is the usual drawback of any fermentation process. Now, lactic acid and alkyl lactates can be catalytically produced from lignocellulosic raw material, cellulose and sugars, as well as from trioses, which are intermediates formed from sugars. If water is used as solvent, lactic acid is formed, whereas in alcohol solvents lactates are generated. Lactic acid has been catalytically produced using metal salts either under subcritical conditions or at lower temperatures. Furthermore, strong alkali was used as a catalyst under subcritical conditions in the production of the lactic acid. Several feedstocks has been applied: lignocellulosic feedstock, cellulose, disaccharides as for example sucrose, monosaccharidic sugars, trioses, C2 containing glycoaldehydes, even glycerol. Trioses, dihydroxyacetone and glycerol aldehydes are formed via retroaldol condensation from sugars, whereas glycolaldehyde is formed from the degradation of the glucose to C2 to C4 aldoses. Glycerol is a particularly interesting feedstock, being a byproduct from the biodiesel production with currently low value. Okay. There are lot of discussion about how to convert glycerin to value added products. Okay. We have already discussed it. Now, typically lactic acid production in high yields is more demanding from the lignocellulosic feedstock than from the sugars. Lactic acid has been produced directly from the lignocellulosic biomass under subcritical water in the presence of homogeneous metal ions. Under subcritical temperatures, in the presence of metal ions, organic material is dissolved, since water is ionized and act as a Bronsted acid. Cellulose transformations to lactic acid have been investigated using several types of heterogeneous catalysts, zeolites, sulfonated carbon, sulfonated zirconia, tungstated alumina and heteropolyacids. The reaction mechanism for formation of lactic acid from cellulose proposed by Holm et al. Consists of cellulose autoprotolysis to soluble oligomers in the first step. Now, this implies that at 190 degree centigrade the pKw of water, okay, the ionization constant of water is low, and thus due to autohydrolysis water acts as a Bronsted acid. Thereafter, solid Lewis acid sites interact with the C3 hydroxyl in the oligomeric glucose unit, leading to dehydroxylation. In the final step, the Lewis acid is cleaved away. Since high reaction temperatures and pressures are needed for the cellulose transformation to lactic acid, the catalyst stability is a very crucial factor. Several carbohydrates and sugars have been transformed to lactic acid using either harsh conditions with subcritical water or milder conditions and homogeneous metal salts as catalyst. Lactic acid has also been produced from trioses either under hydrothermal conditions with the aid of metal salts or alkali, or alternatively using heterogeneous catalyst at lower temperatures such as 140 degree centigrade. Trioses are intermediates in the production of lactic acid from biomass formed during retroaldol condensation of sugars. Hydrothermal conditions in the presence of metal ions have been applied in the transformation of trioses to lactic acid. High yields of lactic acid were obtained also from the pyruvaldehyde under hydrothermal conditions in the presence of metal ions. heterogeneous catalysts are more attractive compared to homogeneous ones. We have understood that, okay, we have discussed why it is so. From the industrial point of view, there are several heterogeneous catalysts which has been reported to be efficient for the production of lactic acid from triages, okay, such as this SN beta, SNSI, CSM carbon mesoporous silica hybrid material and HUSY. Lactic acid formation from glyceraldehyde, which is an isomer of dihydroxyacetone, is slower than from dihydroxyacetone as the substrate when the yields of lactic acid within the same reaction time are compared. Alkyl lactates have been produced using both homogeneous and heterogeneous catalyst. The reaction involves dehydration of triose to pyruvaldehyde followed by esterification of pyruvaldehyde hemiacetal, which thereafter can form either methyl lactate or alternatively the dimethyl acetal of pyruvaldehyde. Okay. Now, lactic acid is an attractive raw material for its conversion to various chemicals. The primary classes of these reactions are hydrogenation, dehydrogenation, dehydration, condensation, esterification, polymerization and substitution at the alcohol group. Lactic acid serves as a highly attractive building block for the synthesis of such chemicals such as acrylic acid, pyruvic acid, 2,3-pentanedione, lactic acid esters and 1,2-propanediol. So, now we will discuss about polylactic acid. The quality of the monomers of lactic acid and lactide as well as the chemical changes induced during polymerization and processing are crucial parameters for controlling the properties of the resulting PLA products. The recent growing interest for the manufacturer of the biodegradable plastic necessitates a high demand for lactic acid as the raw material for PLA production. Much research effort is currently focused on the modification of polylactide to make it suitable for the wide range of applications. Optically pure lactic acid is necessary to obtain high crystalline polylactic acid, which leads to the high strength, chemical and heat resistance properties of the polymer. So, PLA is the first commodity polymer produced from annually renewable sources. PLA is representative bio-based plastic that is used in packaging, stationery, containers, etc. In addition, the utilization of the polyester has been expanded to medical field for drug delivery, resorbable sutures and as a material for medical implants and other related applications. The rate of degradation of PLA depends on the degree of crystallinity. As the lactide content increases, the degradation of the graft polymer decreases. The PLA is a semi-crystalline polymer with a glass transition temperature between 55 to 59 degrees centigrade and a melting point of 170 to 180 degrees centigrade. It shows good mechanical stiffness, high Young's modulus, thermal plasticity and has a good processability. PLAs are basically synthesized via three processes: production of lactic acid by microbial fermentation, second purification of lactic acid and preparation of its cylinder, a cyclic dimer, that is lactide, then third polycondensation of lactic acid or ring opening of the polymerization lactides. So, next figure shows the reaction mechanism for both the polycondensation of LA and the ring opening polymerization of lactides. In direct condensation, a solvent is used and higher reaction times are required. The resulting polymer is a material with low to intermediate molecular weights. Lactide is obtained by the depolymerization of low molecular weight PLA under reduced pressure to give L-lactide, D-lactide or mesolactide. So, let us understand what is the scheme basically. It is a schematic representation of the PLA synthesis. We will start with the lactic acid. So, two routes has been shown here. Okay. Condensation, it gives low molecular weight pre-polymer and upon addition of the chain coupling agents, it gives the high molecular weight PLA. Another route is the condensation, lactic acid to condensation. Okay. Then it gives the low molecular weight pre-polymer. Upon depolymerization, then it gives lactide. That is what we just discussed. Okay. Now, this lactide, when you ring open it, okay. So, undergoes the ring opening polymerization reaction, it gives to PLA, high molecular weight PLA. Okay. The different percentages of the lactide isomers formed depend on the lactic acid isomer feedstock, temperature and catalyst. Polylactic acid can undergo cationic ring opening polymerization. It has been found that trifluoromethane sulfonic acid, okay, and methyl trifluoromethane sulfonic acid are the only cationic initiators to polymerize lactide. The polymerization proceeds via triplet ester end groups instead of the free carbonium ions, which yield at low temperatures an optically active polymer without racemization. Now, the chain growth proceeds by cleavage of the alkyl oxygen bond. The propagation mechanism begins with positively charged lactide being cleaved at alkyl oxygen bond by an SN2 attack by the triplet anion. the triplet end group reacts with the second molecule of the lactide again in a SN2 fashion to yield a positively charged lactide that is opened. Then the triplet anion again opens the charged lactide and polymerization proceeds. Anionic lactide polymerization proceeds by nucleophilic reaction of the anion with the carbonyl and the subsequent acyl oxygen cleavage. This produces an alkoxide end group which continues to propagate. Ring opening polymerization of the lactide needs a catalyst, but it results in a PLA with a high molecular weight. Depending upon the monomer used and the reaction conditions, it is possible to control the ratio and sequence of the D and L lactic acid units in the final polymer. Some sort of process optimization of the reaction conditions. The ring opening polymerization of the lactide can be carried out in melt or solution by cationic, anionic and coordination mechanisms depending on the initiator utilized. The most considered active initiator for the L lactide ring opening polymerization is the stannous octet, which causes a low degree of racemization at high temperatures. It is catalyzed by transition metals such as tin, aluminum, lead, zinc, bismuth, iron and yttrium. PLA is chemically synthesized by heavy metal catalyzed ring opening polymerization of lactide, which in turn is derived from fermentation lactate. However, the trace residues of the heavy metal catalyst are unfavorable for certain applications, in particular medical and food applications. For this purpose, enzymes are attractive targets because they are natural non-harmful catalysts that can derive the reactions under mild conditions. In addition, highly specific enzymatic reactions and or whole cell systems bearing them may be capable of synthesizing polymers with a fine structure from inexpensive raw materials. The appropriate strategy would be the discovery of a PLA producing microorganism. There is no information available on PLA production using natural strands. People are still working on this particular aspect. However, engineered strands have been used extensively for producing LA based polyesters. In that case, the lactobacillus strain could be useful in establishing the one step process for the synthesis of the LA based polyesters. So, with this I conclude today's lecture. See, in our next class we will be discussing about succinic acid, propionic acid, acetic acid and butyric acid. So, thank you very much. In case you have any query, please register in the Swayam portal, or you can always drop a mail to me at kmohanty@iitg.ac.in.